Hi everyone, part 4, electric field lines and electric potential. So, electric field lines. Okay, what are these things? These are simply vector arrows used to represent the electric field. We talked about them last time, last section. Okay, now remember, the density of these lines represents the magnitude of the field. The closer that the lines are together, the stronger the field. So let's talk about, last time we talked about just single charges. Remember, when we have a negative charge, the electric field goes in to the negative charge. Now, in this situation, we're going to talk about when there's two negative charges. Okay, so remember, the electric field goes in, but what happens in the space between? So what happens is the electric field lines interact with each other, which is what gives it the repulsive force. Okay, so what ends up happening is the electric field lines go like this. They do not interact in the middle, okay, and it's this non-interaction of those lines in the middle that gives us the repulsive force in the end. Now look, it's all relative, but if I draw more arrows here, it just means that there is a stronger electric field. Okay, that could of course be caused by increasing the charge on the two objects or even the one object, and it could also happen if you put the two negative charges closer together. So if we have a positive and a positive thing going on, remember we go out of positives, the electric field does. And what happens in the middle? Well, of course, one goes out, the other goes out. These, again, are repulsive. So instead of interacting, they bend each other, like so. And then the result is a repulsive force. Okay, awesome. Then, of course, with a positive and a negative charge, remember, we go out of a positive and into a negative. So out of a positive, into a negative. And what happens in the space where they interact? Remember, this is an attractive force. So we go out of the positive and into, oh, look at that. That line, okay, it goes out of the positive and into the negative. Okay, so the electric fields interact in a way that attract each other. Okay, again, the more lines we make, the stronger the electric field is. All right, so let's talk about conductors and electric field lines. Now, we've talked about this before, but just in terms of the electric force on objects. Okay, let's talk about it in terms of electric fields. So if I have, there are 5 different situations, or 5 possible scenarios, okay, or situations. Okay, the first one is if you have a solid conductor. Okay, so let's just draw kind of a circle here. So a solid conductor. Okay, what happens with a solid conductor? Okay, the electrons on the solid conductor want to get as far away from each other as they possibly can. So let's just draw 4 just for the fun of it. Okay, so 4 and those are electrons, remember. Electrons have negative or are negative charges, so of course they bring in an electric field. And what ends up happening is we get a uniform electric field around this object because of its electrons. Okay, all going in. Of course, if you increase the charge, so if you put more electrons kind of on the outside shell, you get more lines, so a stronger field, which means that it'll generate a stronger force. Okay, so that's a solid conductor. Okay, solid round, I guess. What if we had a solid flat conductor? Okay, now you've seen this picture before. So you have a solid flat conductor. Remember, the electrons want to get as far away from each other as they possibly can. Okay, that gives us that static force. The electrons are trying to get as far away from each other as they can. So of course that gives us, it's negative again, so the electric field lines are going in. And we get this fairly uniform electric field around the solid flat conductor. Okay, again going in. Okay, the next one is irregular shapes. Now the one we used before was an irregular kind of pointy object. Now remember, the electrons, the charge builds up closer to each other on the pointy end of a irregularly shaped conductor. So you get the negatives there, they're kind of close together, and then they spread out a little bit on the edges. Okay, so remember, the charges tend to accumulate at the points. So if we draw the electric field lines here, see how the electric field lines are closer at the point than they are further away. So if we put more electrons on here, okay, we can really see that the arrows are quite dense around the point. Okay, so of course that means there's a stronger electric field, which of course makes a stronger electric force at the points of an irregularly shaped, wow, I missed an R up there, irregular shaped object. Okay, awesome. Now let's talk about a hollow object. So remember those? Remember the hollow objects, the charge built up on the outside but not on the inside? So you get the electric charges building up on the outside. These are the electrons. Remember, the protons are stuck. Okay, so we get a uniform, well, I shouldn't say uniform, we get an electric field around there. Now remember, the further away from the object, okay, the less in magnitude the electric field is, which means the less the electric force is, the further away. For instance, if I put a positive test charge here and a positive test charge there, this positive would feel a much greater force than would the further away one. And remember, that's from that formula KQ1 Q2 over R squared. That R makes a huge difference. Okay, now, so remember, there is an electric field surrounding the outside of this object. But remember, if this is hollow, there is absolutely, remember, the electrons are all pushed to the outside edges, so there is no electric field inside the hollow object. So no electric field, no electric force on the inside of the hollow object. Okay, now these four are all, kind of interesting, but where this physics gets really cool is when we introduce charged parallel plates. Like, that's when life got interesting for physicists. Okay, so when we had two charged plates, and the way they charged them, they made a battery. Okay, and we'll talk about how they did that later. But for right now, let's just, okay, so when we draw a battery, we draw kind of these small lines and large lines. The small lines are the negatives, the large lines are the positive. Remember how a battery has a positive terminal and a negative terminal. Okay, so we connect one of these parallel plates to the negative side of a battery. Okay, and that makes this parallel plate negative. Okay, and then we connect this one to a positive plate, and that makes this side positive. Now, it doesn't deposit positive charges, it just takes all the negative charges, right? That's how you get a positive anything. Okay, so what ends up happening, now, sorry, these are positives, that's not, with that line in there, it kind of hides it a little bit. Now remember, electric fields go out of positives and into negatives. And it just so happens that in the middle of parallel plates, remember how I was talking about if you drop a positive thing here and a positive one there, okay, the closer one feels a much stronger force because the electric field is stronger closer to the object. In parallel plates, and you know what, around the edges you get some weird kind of bulging of the line, so it's a little bit weaker around right around the edges. But in the middle of these parallel plates, what ends up happening is the electric field is uniform, which means it's exactly the same. If it's 5 newtons per coulomb, it's 5 newtons per coulomb here at the positive plate, and it's 5 newtons per coulomb here at the negative plate. And it opens up a whole new realm of physics for us, so we'll get to that later. But these are the 5 possible situations for conductors and electric field lines. It's really quite cool. All right, moving on. Okay, so let's talk about electric potential energy. Okay, the change in potential energy is the same as the amount of work done. When dealing with electric charges, work is required to move like charges away from each other. Sorry, not my bad. Work is required to move unlike charges away from each other, right? Unlike charges want to get close together. So if you have a positive and a negative, okay, they are attracting each other. So if I pick up the negative and try and move it this way, it's going counterproductive to what it wants to do, so I have to do work. It's kind of like holding a pen up. If I want to lift that pen up, the pen wants to go towards the center of the earth, which is why when I drop it, it falls. Okay, so if I want to move it away from its natural tendency, so move the pen up, I have to do work. If I want to move this negative charge away from the positive, I've got to do work. If I want to move a positive away from a negative, I have to do work. Now, with like charges, if I move 2 like charges closer together, they don't want to be closer together, so then I have to do work with those as well. All right, anyways. Okay, so pardon me, I'll try and fix this, but in case I haven't yet. So work is required to move unlike charges away from one another. It can also be described as the stored potential energy between 2 like charges at a distance apart, or 2 like charges that are next to each other. So, as with gravitational potential energy, a reference point is required, right? Usually for gravity, we use the ground. Okay, how much potential energy do you have with respect to the ground? Here, okay, how much potential energy do 2 unlike charges have when they're right next to each other? What about if one of them was at an infinite distance? Would it matter if the charges were like or unlike at an infinite distance? What about when they're right next to each other? Okay, so let's talk about this. Okay, if you have a positive charge here and another positive charge there, and you stuff them really close together, okay, let's fix this one. So let's say this left guy can't move, but we leave them and we let go of the one on the right. Okay, so that's a positive. If I let go, that's going to go, it's going to spin out that way because he doesn't want anything to do with that other positive charge. So by putting that positive or these 2 positive charges together, we have to do work. We have to give a lot of potential energy, okay, to force these 2 charges together so that when we let go, the positive charges repel each other and the one charge just gets kicked out. Okay, the same thing happens with 2 negative charges. Okay, if I put 2 negative charges close together, they don't want to be anywhere close together. So when we let go, they will repel each other and move away from each other. So to put them close together, you had to do a lot of potential, or you had to add a lot of potential energy. Okay, so when you let go, remember that potential energy turns into kinetic energy, which of course is the energy of motion. These things move away from each other. Now, if we put these 2 charges an infinite distance away from each other, okay, so these will attract each other, but they're really, really far away. So the force involved here isn't very much. These guys do not have very much potential energy with respect to one another. And that's the same if I have 2 positive charges that are really, really far apart, like infinity apart. Okay, they really don't have any potential energy or any kinetic energy with respect to each other. They're just really far apart. All right, so remember that if an object is being held at a distance, it has potential energy. Okay, if I have to hold it, which means it doesn't want to stay there, then it has potential energy. As soon as it is released, that energy is converted into kinetic energy. And again, this is assuming we have an isolated system, no external forces act, no matter comes in, no extra energy comes in, okay, that kind of thing. Okay, so the speed at which the particle is traveling can be determined using this relationship. Remember, okay, the change in potential energy is going to be the change in kinetic energy, so that's going to be EK. Now remember, the EK formula is still 1/2 mv squared, but EP, we can't just use mgh anymore because that's gravitational potential energy. We're going to be talking about electrical potential energy now. Okay, so in bold here we have electric potential. Okay, so that's the electric potential energy stored per unit of charge at a given point within an electric field. Okay, sure, why not? Okay, so electric potential difference, that is the change in electric potential energy when a charge is moving within an electric field parallel to the field. Remember, we have to be parallel because if the field is going this way, right, between say a negative and a positive charge, actually it would be a positive on top because out of positives into negatives. Okay, so if I want to move a positive charge, remember the positive charge is going to want to go towards the negative and away from the positive. If I pick him up and move him there, I have to give potential energy, right? But the thing is, if I move that positive charge this way and put it here, I'm not fighting the field, right? I'm not fighting the electric field, so no work is being done. It's like moving a pen sideways with gravity, right? So if you have the ground here and an object there, if this is 1.00 meters, if you move that this way so that it's still 1.00 meters above the ground, you're not changing its gravitational potential energy. Okay, same thing with electrics. All right. Maybe that's clear. Hopefully that's clear. If it's not, feel free to rewind, or hopefully just bear with me. Hopefully the examples will make more sense. Don't worry, we'll get there. All right, so let's talk about calculating the electric potential difference. Okay, so remember electric potential difference. Okay, this is change in potential energy, so this is voltage. Okay, so delta V is equal to delta EP, so change in potential energy over Q. So V is the electric potential, and that's measured in volts. Okay, you guys have heard of like a 9-volt battery, like your 12-volt battery in your car. Okay, so that's the voltage, the electric potential between the two electrodes. Okay, EP is the electric potential energy, and that could be measured in joules, or this new thing called electron volts, and we're going to talk about them here right away. And of course, Q is the magnitude of the charge, just like it always has been. Okay, so let's talk about this electron volt thing. Now, electrons have extremely small charges, okay, as do protons, as do a lot of the subatomic particles. Okay, so because they're so small, and because the charges are so small, okay, we have to use scientific notation an awful lot. So when we have these really small energies, okay, we sometimes divide them by the elementary charge or the charge on an electron to get units that we don't have to say times 10 to the negative whatever quite so often. Okay, so there's a really simple relationship here. 1 electron volt is equal to 1.60 times 10 to the negative 19 joules. Okay, it's just a simple little relationship, okay, and it just makes the notation easier for scientists. That's all it's about, so don't stress over it too much. All right, so let's look at the practice problems, and hopefully these will become more clear to you. Okay, so number 1, in moving a charge of 5.0 coulombs from one terminal to the other, a battery raises the electric potential energy of the charge by 60 joules. Determine the potential difference between the battery terminals. Okay, Okay, so remember, a battery gives potential energy to the electrons so that they can do work to power your phone, your tablet, your MP3 player, your computer. I don't know, pick a device. Okay, but that's how batteries work. All right, so here's the formula. So delta V is equal to delta EP, so change in potential energy, over Q. All right, so I'm raising the potential energy of these electrons by 60 joules, and we have 5.0 coulombs worth. Okay, so that works out, 60 divided by 5 is 12. Now that's technically a joule per coulomb, but the funny thing is, a joule per coulomb is a volt. So this is 12 volts. Wow. Okay, so that's not a hard formula to use. So 12 volts, awesome. Okay, moving on, number 2. All right, so a charge of 2.00 times 10 to the negative 2 coulombs moves from one charged plate to an oppositely charged plate. The potential difference between the plates is 500 volts. How much electric potential energy did the charge gain? Okay, so a charge of that moves from one charged plate to the oppositely charged plate. Okay, the potential difference, 500, so we're looking for potential energy. So voltage is equal to EP over Q. So if I want the potential energy, so I multiply the Q up, so delta EP equals delta VQ. Awesome. So my voltage was 500 volts. My charge is 2.00 times 10 to the negative 2 coulombs. Okay, so 500 times that, that's these 3 sigdigs worth. So that works out to 10.0. And remember, electric potential energy, or all potential energy, is measured in joules. Okay, so 10 joules worth, 10.0 joules. Okay, awesome. Good, good. Number 3, a small charge of 3.2 times 10 to the negative 19 coulombs is moved between 2 parallel plates from a position with an electric potential energy of 2.0 times 10 to the 3 volts to another position with an electric potential energy of 4.0 times 10 to the 3 volts. Okay, so let's look at what's going on here. See, you have a positive charge, and I pick him up and I move him away from the negative. He wants to be closer to the negative, and I move him closer to the positive. He doesn't want to be closer to the positive. So I am increasing its electric potential energy, right? I have to do work to make this positive charge go somewhere it doesn't want to. So I provide work to that. Okay, so now I have to find the potential difference. So that of course is the voltage between the two positions. Okay, well, remember the voltage, the delta V here. Okay, remember that's delta anything is always the final minus the initial. So the funny thing there is the final voltage is 4.0 times 10 to the 3 volts. And the initial is 2.0 times 10 to the 3 volts. Remember, times 10 to the 3 is 1,000. So this is 4,000 volts minus 2,000 volts. Well, hey, that's just 2,000 volts. So I have given this thing, okay, 2,000 volts of, well, it's not really energy, but that's the idea. I've increased the voltage or changed the voltage by 2,000 volts. Now, B, the electric potential energy gained by the moving charge in joules and electron volts. Okay, so I need to know the electric potential energy gained. So remember, delta EP, okay, we've already rearranged that up here, right? See up here, right, on number 2. So delta EP is delta VQ. So I have changed the voltage by 2,000 volts. And I have a charge of 3.2 times 10 to the negative 19 coulombs. Okay, so what's going on is I have given this thing 6.4 times 10 to the negative 16 joules of energy. I had to do that much work and give the charge that much potential energy to get it to move closer to the positive plate. Remember, it doesn't want to be anywhere close to the positive plate, right? Positive charges do not like each other. All right, so this is what I was talking about with the whole units. So the electric potential energy here, so 6.4 times 10 to the negative 16 joules. Okay, when you say times 10 to the negative 16 like a million times in your career, you're going to get a little grumpy about it. So that's why scientists invented this whole electron volt thing. Okay, so what we have to do, remember 1 electron volt is 1.60 times 10 to the negative 19 joules. Okay, so then we go x electron volts over 6.4 times 10 to the negative 16 joules. We cross multiply and divide. Okay, really all you're doing here is you're dividing this joules by 1.60 times 10 to the negative 19. Sorry, that's not really clear on this negative 19. Well, still not great, but you get the idea. Okay, and then so X, which of course is the electric potential energy, is 4.0 times 10 to the 3 electron volts. So it's a small e, capital V. Okay, and remember, electron volts is an energy. Okay, so 4.0 times 10 to the 3 electron volts. Okay, and it's just a little bit easier working with these numbers as opposed to 10 to the negative 16. Okay, negative 16, like that's unfathomable how small that is. Whereas 4,000 of anything, at least you can kind of wrap your brain around that. Okay, just a couple more examples and we'll be done this section. So number 4, a sphere with a charge of magnitude 2.00 coulombs is moved between two positions between oppositely charged plates. It gains 160 joules of electric potential energy. What is the potential difference between the two positions? Okay, so tell you what, let's just draw a quick picture here. So we got these parallel plates. Let's say this guy's positive, this guy's negative. Okay, awesome. Okay, so we've got a charge of 2.00 coulombs. Now look, there's no negative on that, so that means it's positive. Okay, so look, if I just draw that kind of in the middle, if I am gaining 160 joules of potential energy, that thing, I have to do work on it to gain or increase the potential energy, so I'm actually moving it this way, closer to the positive plates. Okay, anyways, not that that matters, it doesn't really ask that in the question, but I just want to give you guys an idea of what's going on. If I'm increasing its potential energy, I'm moving it against where it wants to go. All right, because if I just let it go, right, it would get repelled by the positive and attracted by the negative, and it would go down. So then it would lose potential energy and gain kinetic energy. Well, if it's gaining potential energy, that means I got to be moving it against the grain, okay, so towards the positive. Okay, so what is the potential difference? So that's the voltage. So remember, delta V is equal to delta E P over Q. Okay, so we are giving it 160 joules of potential energy, and it's 2.00 coulombs worth. Okay, so that is going 3 sig dig, so 80.0 volts. So this thing is in between the parallel plates of an 80 volt, oh wow, I guess you could say battery if you really wanted, but the difference between the two plates is 80 volts. Okay, number 5, an electron moves between two positions with an electric potential difference, of 4.00 times 10 to the 4 volts. Determine the electric potential energy gained by the electron, expressed in joules and in these electron volt things. Okay, well, sounds easy enough. All right, so how this works, so potential energy. Okay, so remember the formula is delta V equals EP over Q. So, of course, the Q multiplies up. So, delta EP is equal to delta V times Q. Okay, so our voltage is 4.00 times 10 to the 4 volts. Okay, times the Q here. Q for an electron is 1.60 times 10 to the negative 19 coulombs. Awesome. Okay, good, good. So when we multiply this out, we get 6.4 times 10 to the negative 15 joules. Okay, so if I want joules, okay, or if I want electron volts from this, remember, 6.4 times 10 to the negative 15 joules divided by 1.60 times 10 to the negative 19 joules per electron volt. Okay, we can do it that way. And oh, look what happens here. 4.00 times 10 to the 4 electron volts. Now let's just talk about what an electron volt is again. Remember, that's the amount of energy that one electron gets from 1 volt. Well, look, if an electron, oh, look at that, electron goes through 4,000 volts, the electron gains 4,000, 10 to the 4, so that's 40,000, pardon me, 40,000 volts, then we gain 40,000 electron volts of energy. Wow, electron through a volt, electron volts. Okay, anyways, so 40,000 or 4.00 times 10 to the 4 electron volts. Crazy. All right, guys, I want you to practice this stuff. This is 11.2 in your textbook, electric field lines and electric potential. So I'd like you to do number 2, and then 4 through 10. Starts on page 569 in your textbook. You can go right out of your textbook, or you can print off the document or that page that I included in your workspace card. So good luck, and as always, if you need any help, your teacher is there to support you, and we'll go from there. See you next section.